Welcome back to Codex. Today we have Hannah Lawrence from MIT. Hannah's an expert in symmetry-aware machine learning. Today she'll tell us about polynomial learning problems. Take it away, Hannah.
Awesome. Thanks so much, Dustin, for the invitation. I'm really excited to speak at the Codex seminar. Looked like you had a great lineup of previous talks. So yes, I mostly work on equivariance, and as Dustin mentioned, today I'll be speaking about learning polynomial problems with SL2R equivariance. And this is very much joint work with my collaborator from MIT, Mitchell Harris, who's actually also on the Zoom. So hopefully we can have an extra line of defense if there are any particularly tricky questions. I'm joining from the computer science department and Mitchell is joining from the math department. So let's get started. So the fundamental problem that will be the subject of the talk is polynomial positivity. So very simply, if I give you a polynomial, is it positive for all x in the domain? So for example, this polynomial is a yes, that is positive. It does not cross below the x-axis in this one-dimensional case. This polynomial is not positive. That is the question. And in particular, we want to be able to prove that a polynomial is positive. And this might seem like a sort of bizarre primitive, but it actually has a ton of applications across robot path planning, dynamical system stability, designing nonlinear controllers, and beyond. It's really considered a fundamental primitive sort of in the polynomial and optimization world. And in particular, let's zoom into this verification part. So what do I mean by proving that a polynomial is positive? So first, let me say we're going to deal with bivariate polynomials in this talk, although the ideas can be probably pretty easily extended to having more than two variables. For now, we'll deal with just x and y. So when you see a vectorized x, I really mean x and y. And let me just set up some notation that we'll be using in the rest of the talk. So first, we'll define the d left, which is a d+1 length vector of monomials, and it basically covers all of the possible monomials that would occur in a bivariate homogeneous polynomial of degree d. And we're going to say that a matrix M represents a polynomial P in XY if analytically the following equation is true: P of XY is equal to this quadratic form between the d lift vector and this matrix of constants M. So pictorially, this looks something like this. And we're claiming that matrix M, or we're stating that a matrix M represents a polynomial P if treating X and Y as symbolic variables, this equality holds. So if a matrix Q represents P and Q is symmetric and positive semidefinite, it's immediately clear that the polynomial has to be greater than or equal to 0 for all x and y. This is by definition of having an SCP matrix. All the quadratic forms are positive. Another way of looking this is that by looking at the eigenvalue decomposition of M, if it is PSD, this gives you a way of writing P of X as a sum of squares. And of course, a sum of squares cannot be negative. So this is really what we mean when we talk about verifying that a polynomial is positive. We want to find one of these representing matrices, which in fact is also PSD. And if you can check that the matrix M is PSD and it represents P, then P is definitely a positive polynomial. So this is the unit of currency that we're going to care about in this talk. And I just want to note that representing the polynomial is very simply a constraint on the antidiagonal sums of this matrix M. And what that implies is that for a given positive P, there are many such M which can represent it and can be a verifier of its positivity. And there's a convenient choice that we'll work with in this talk, which is set up as the following the solution to the following optimization problem. In particular, let's choose the matrix Q, which represents the polynomial P and is positive semidefinite. And so those are like the basic requirements, but also has maximal log determinant. You might ask why you should do that. One is that this is established as the analytic center of the feasible region of such matrices, so we're avoiding the boundary. Another thing you can verify is that it has a unique solution if P is positive, so it's all well defined. And finally, there will also be some equivariance properties that are basically about to explore, which are sort of provide a very desirable structure for this optimization problem. So to recap, we have a polynomial P. We want to prove it's positive if it really is positive via a matrix Q. Really, any PSDQ that represents the polynomial will do. However, we have to pick one. Well, for the sake of generating training data, which I will discuss, we have to pick one. And so we're going to pick the Q of maximal log determinant, which has some desirable properties. However, what's wrong with the way of typically solving this problem? So I guess I maybe skipped here. Let me go back to the punchline here. Typically, you can solve this via convex optimization. And so you could ask, well, what is there to do with this problem? It's sort of solved. We know how to solve it. If I give you a problem, you can get an answer. The problem is that STPs are slow and scale poorly with degree. And so for higher degree polynomials, verifying positivity cannot really be done efficiently in this manner. And in this talk, we'll explore a possible acceleration with, you guessed it, machine learning. So question one you might have is, why do we think that ML could help? Why would we be so bold to assume it would have something to bear on this problem? And indeed, this might seem like a lot to hope for, because in general, positivity verification is in fact NP hard. So it can be reduced to problems in combinatorial optimization. However, we like to say in the machine learning community here that that hope is not really lost, because you might have a specific data distribution, for example. If you only care about solving this problem on a specific data distribution, which perhaps has some extra structure, for example, a really sort of trivial example would be, what if your whole data set, like in your robot path planning applications, all the polynomials that you care about verifying positivity for, the ones that are actually positive, are actually just squares of another polynomial? This should be a lot easier. This should no longer be an NP hard problem. And so throughout the talk, we're not going to really explicitly specify the form of such a distribution, but mostly use it as a high-level guiding intuition that there is still some hope of accelerating this positivity verification problem, subject to what your data distribution is. And our sort of ansatz here is that it's still worth doing, because real-world data distributions hopefully will have this kind of structure to them. There's also a track record across many other fields of machine learning accelerating slow computation. So I have to say, when Mitchell and I were looking through the literature, we really couldn't find too much that sort of used machine learning for this style of problems where the data types are all polynomials. But there's a very, very rich line of research in the machine learning for science world of basically training neural networks as a way of accelerating slow computation, almost like sort of automatically discovering a faster algorithm, or maybe just a reduced order solver. So for example, one that I'm more familiar with comes up in catalyst discovery, where basically density functional theory can be used to model how atoms in a system will evolve over time by predicting sort of a per atom force, but they're quite expensive. And so one pretty successful approach for speeding up density functional theory, which by the way you want to do so that you can try tons of different possible materials and see which ones actually interact in the way that you want them to in a system and which ones don't, and hopefully discover a new catalyst. One way that this is accelerated so that you can really screen tons of catalysts at once is training on a bunch of expensive DFT calculations. So training some small neural network and then using that trained model on new data as sort of a faster, slightly lower accuracy substitute for density functional theory. And so this has been actually like very successful in this field of chemistry, of computational chemistry. And there's another desirable property in this application too. So I'm going to take the analogy one step further, which is that if I give you one of these proposed catalysts, you can actually then verify it using the full expensive computation of density functional theory. So if I find a good molecule for you, you can actually check that I'm not lying, that it really is good. But you've used this acceleration to sort of come up with a good catalyst. And I want to sort of use that as a guiding analogy for this positivity verification problem. So the problem is different, the applications are different, but our underlying idea of training on expensive computations, which are coming from convex solvers, and then sort of using that trained model as a substitute for those convex solvers on new data, is what's going to guide us. And once again, we'll have this verification property. So let's just set up this pipeline really simply. I give you a polynomial. You want to know, is it positive? So we're going to feed it into this network that you've trained on a bunch of convex solves. The network is going to spit out a matrix M, which we'll see in the construction of the network, it is by definition going to satisfy that it represents the polynomial in this way. So now you check, okay, is M positive semi-definite? If it is, you're done, you're good. You've checked that the network was not lying to you. And if it's not, maybe you imagine then putting it into an STP solver. So if it fails, you can sort of gracefully fall back to an existing solver, but when it succeeds, you can check it and there's no room for uncertainty. And this is sort of a luxury that honestly we're not really used to thinking about in, say, computer vision or other applications. So the next question, and where we'll finally get to the equivariance part of this talk, which was really my bread and butter, is what kind of machine learning should we try for this problem? So if you stare at this problem for a little bit, because of the way we framed this maximum long determinant objective function, the problem exhibits symmetry. So your input is a bivariate, again, it's a bivariate polynomial P, and your output is supposed to be this matrix Q that satisfies this optimization problem. If you now apply a change of variables to X and Y, so A here is a 2x2 matrix, the output transforms in a very well-defined linear fashion relative to the original output. And so we've written this in terms of this induced matrix, which is no longer 2 by 2. We've taken the 2 by 2 matrix A and added the superscript D, and it's basically defined as written in the equation on the left with some sort of complicated nonlinear equation that you could write out. But the important thing to note basically is just that this problem exhibits a symmetry in that if you change variables in the input polynomial, the optimal solution to this problem, which again, recall is unique, transforms in a predictable way. Now, what I just wrote sort of holds for all, any general GL2R invertible matrix. This is a really large group. And for the types of tools that we're used to using in equivariant learning, it's a little bit easier to look at a subgroup instead, which is still very challenging, but is just slightly nicer changes of variables A. And that's going to be the special linear group SL2R. So this consists of 2 by 2 matrices that are of determinant 1. So of course they're invertible because the determinant is non-zero, but they're also area preserving in the sense that, again, the determinant is 1. So for example, as shown on the previous slide, this group acts on the vector space of bivariate polynomials, which we'll consider a vector space in terms of just the vector of its coefficients, by basically doing a change of variables on the symbolic variables x and y. And just to see what this looks like pictorially, here we're representing this polynomial. It's in x and y, and then the z-axis is indicating the value of the polynomial at that x and y. And the red dots are local minima, and the blue dot is the global minimum. When the group elements that are shown here in the 3 panels act on this polynomial, they're sort of stretching it out in the direction that's governed by the group element. So in this case, although we're not working with the simpler problem of polynomial minimization, the global minimum is shifting, or the minimum value is invariant, but the location is equivariant. And so actually a lot of the machinery that we'll discuss in terms of building an architecture holds for these sorts of minimization problems, but we see sort of more interesting behavior and are also a little bit more excited about the positivity verification problem. So that's where we will focus our attention, but you can check the preprint, which just went up on archive, for details of like some experiments on this minimization type problem. But suffice it to say, this is the special linear group. It acts on polynomials, and it's very relevant for this problem. It provides a ton of extra structure. So how do we take into this account this structure when we're building this neural network to approximate this optimization problem? So I don't think I have time to really give a proper primer on equivariant learning, and I'm hopeful that people have seen at least a little bit of this before, but let me at least remind you of the main idea. So we start, in general, the idea of equivariant learning is that you have a group G and you have 2 group representations which act on the input and output space of some function. So f goes from x to y. Row 1 and row 2 are basically just describing how the group transforms x and y. And the function f from x to y is equivariant if transforming the input induces this transformation in the output. So we have one of our little commutativity diagrams that people in this field, I'm sure, have seen a lot. X maps to f of x. That's just the definition of f. But if you transform x according to the group, the output of this function also transforms. And this, of course, again, comes up in lots of fun applications like predicting energy and forces from a molecular system. If you rotate the input, you should either be rotating the output in the case of forces or preserving the same output in the case of energy. And so, okay, this was our commutativity diagram. Now for our problem, our inputs are now polynomials, our outputs are matrices, but it's basically the same story. When we perform a change of variable on the input polynomial, we want this sort of conjugacy transform to happen to the output matrix. And this is something that we'd like to build into the network. In fact, so a network can also be equivariant, where this arrow that's the ground truth function we're replacing with a neural network, and it may or may not learn the exact function, but let's at least make sure it has the same fundamental structure as the correct problem does. So we're going to try to be SL2R equivariant, and I will foreshadow that we will succeed, but also fail in a sort of surprising way. Now, there are tons of approaches to equivariant learning. I do not have time to go into the details of these, so I'll just generally say there are 2 broad categories with most efforts concentrated in the first category, which is working with compact groups. So any finite groups or the orthogonal group are sort of the typical ones. And there's a whole slew of techniques for working with compact groups. You may have heard of group convolutional networks, sort of tensor product-based networks. There's recently more work on working with non-compact groups, of which SL2R is one. And these sort of can be divided into 2 categories. We have approaches that are not precisely equivariant, but are sort of approximately equivariant. Maybe there's some sort of sampling that's approximating an integral. And then there's also a sort of class of approaches, which I will sort of go into more detail in the context of SL2R, which enforce exact equivariance using tools like tensor products and the Clebsch-Gordon transform. And this should not be, I guess, self-contained, but maybe more of just an illusion for those of you who have seen this before. And I will go into our particular approach for SL2. So what makes non-compact groups hard? Just a few things to sort of keep in mind as we're going through here, and things that may sort of transfer to other non-compact groups as well. Well, one point is that the induced representations can be arbitrarily poorly conditioned. So SL2R acts linearly on these higher degree polynomials, as was shown in the previous slide by this induced matrix. But of course, SL2R includes non-orthogonal matrices. So the 2 by 2 elements of SL2R can already have a condition number that's greater than 1. But in fact, as you consider the way that this matrix acts on higher and higher degree polynomials, it gets exponentially worse conditioned. And so this is one thing that we actually have to be careful about numerically when we're sort of trying to generate training data or transform the training data, which is that unlike in this nice rotation case where sort of condition numbers are always going to be 1, for example, suddenly now we have to worry about having ill-conditioned representations and matrices. And we'll see sort of how that comes up in the sort of final approach that we propose. Another thing that's I think one of maybe the more important ways of thinking about non-compact group equivariance is that you don't actually have a finite Haar measure anymore. So you can't actually sort of integrate over the whole Haar measure in the way that you can, at least without sort of additional assumptions and structure on function decay and such. But really simply what this means is that you may not have the points in the orbit of a given data point all be equally likely. Like this may not be possible. So by orbit, I just mean all of the group transformations of a given input. So for example, consider this vector x, which is 1, 0. You could also think of it as a degree 1 bivariate polynomial, which is just x. And consider these matrices in SL2 acting on this vector. And this is a sort of simple subset of matrices of SL2 that just moves x all along the x-axis. And in fact, the orbit of x is now the entire x-axis. So of course, we can't really have an actual uniform distribution over this orbit. So what does that mean? It means that suppose you often think about taking your training data and then applying one of these group transformations to it. For example, in the case of rotations and molecules, you apply a random rotation to your input molecule. In the case of compact groups, this not always, but almost always doesn't actually change the training distribution. It's genuinely like if you apply a group transformation to your input data, you're getting like a new sample from the training distribution somewhat. However, in the non-compact group case, if you apply an SL2 transformation to everything in your training set, you're actually changing the distribution. And so we now think of equivariant learning as sort of giving us out of distribution robustness in a sense, as opposed to sort of pseudo new samples that you would get from equivariance. So these are sort of two high-level things that we keep in mind when we're working with a non-compact group like SL2 instead of a compact group like SO2. So let's get back to actually building the architecture. So again, we want an equivariant architecture with respect to SL2R. So we want some interesting way of building functions that has learnable parameters and is SL2R equivariant and goes from a polynomial input to a matrix verifier output. And in order to do this, we need some representation theory. And again, if you've seen a lot of equivariant learning before, then this will probably be very familiar tools to you. And if not, then maybe don't worry too much about understanding all of the details, but I hope this gives a flavor of what the sort of typical recipe is for building these equivariant networks. So let's start with a group representation. I've actually already mentioned this. Basically just a function from the group to linear maps on a vector space, in addition to a specification of what that vector space is itself, which plays nicely with the group action or with the group operation. So when we talked about, yes.
Sorry, there's a question in the chat. Why can't you just enforce equivariance on the generators? Not sure what generators are.
Oh, so like the group generators in the sense of like everything in the group, every element in the group can be gotten from a combination of the generators. That would be fine, I think. Which will feel free to jump in if I'm missing something obvious, but I'm not sure why this is not generally the way that we think about it. But I think if you have if you can get equivariance to any group element via the generators, this would, it seems like this would give you group equivariance as well. I see there's like 5 chat. Let me see if I can open these. Yeah, so feel free to, oh yeah, I said Mitchell asked generators. So I guess the thing, maybe you should think about this for a moment longer or respond offline. I think equivariance to the generators would be fine. I'm just not clear on how you get equivariance specifically to the generators alone. I'm not sure if that actually makes it easier, but that it seems like that would be sufficient as well. Okay, I see I'm on the same page as Mitchell. So yeah, this could be an interesting idea, but I think a priori, the sort of tools that we have you don't really get a huge gain from just thinking about the generators. Maybe that would actually have interesting implications for data augmentation. But yeah, thank you for the question, Stephen. Cool. Yeah, and feel free to ask questions throughout, either by chat or unmuting. Anything is totally fine. All right, so I guess returning to our little representation theory tangent here, we also have irreducible representations, which are extra special. Basically, they sort of don't have invariant subspaces. The precise definition isn't going to matter here so much. The important thing is really that they can be used for understanding the other representations of a group. So for all compact groups, and indeed, in fact, for also in the cases we care about for SL2R, we can decompose a group representation into irreps in the sense that you can sort of block diagonalize a representation in the same way over all elements of the group in terms of the irreps. At least for finite dimensional representations. And so understanding the irreps sort of give you like this toolkit that you can modularly rearrange to get out any group representation. And this is why a lot of equivariance literature cares about the irreps. So what are the irreps of SL2R? Well, they're actually the spaces of polynomials, which is a super convenient property since that's the data type that we're working with already. So our input already lives in an irreducible representation space. More formally, for each integer d greater than 0, there's this d plus 1 dimensional vector space of degree d homogeneous binary forms. And this is the vector space of an irreducible representation. So here's an example for d equals 3. And note that all the terms here are degree 3. And we're going to work with a monomial basis. So again, we can translate this particular polynomial to a monomial basis. And so we've now specified the vector space part of the irrep. How does the group act on polynomials? Well, it's actually exactly what we said already. So it acts by this premultiplication of the variables. So this is great. It's driving really well with the particular positivity verification problem. And indeed, our inputs are already in irrep spaces. So that's a sort of convenient way of thinking about things. So in general, neural networks, they have linearities and non-linearities. And by combining these in a bunch of layers, you can approximate interesting things. At least that's the sort of common wisdom. So let's start with the linear layers. I think almost every equivariant network uses the same tool for this, which is Schur's lemma. And it basically says that when you think about, you organize your inputs in terms of irrep spaces, as soon as you have a block diagonal matrix, you're equivariant. So you just need to restrict to this particular sparsity pattern in your learnable parameters. I'm intentionally being a little bit hand-wavy here because I want to get to some other juicy stuff in the talk after establishing the architecture. But roughly, Schur's lemma here tells you exactly what you need to have a linear equivariant mapping between these irrep spaces. So again, our activations of the network are going to live in these different vector spaces. Our activations throughout the network will be polynomials, and we're going to consider linear mappings between polynomials, at least for the linear layer, as determined by Schur's lemma. So again, I'm sorry to rush through this, but hopefully if you've seen it before, this rings the right bell. And if not, at the high level, there's a sparsity pattern. We can get linear equivariance. It's not so hard. How about the nonlinear layer? And again, this is a tool that's used sort of quite often throughout other equivariant architectures for groups that are not SL2R, and indeed it works here too, which is tensor products. So the tensor product is nonlinear in the sense that we're taking a tensor product between basically a thing in itself. So this is a nonlinear function, gives us a way of building polynomials. And for, I guess, the connoisseurs, the tensor product of irreps is itself a representation, which means it decomposes back into irreducible representations. And this precise decomposition for SL2R has actually been studied previously in a sort of disparate, like non-equivariance literature. And it tells you exactly how when you take two of these vector spaces, which consist of different degree homogeneous bivariate polynomials, you take the tensor product of those vector spaces, you get out something which is isomorphic to a direct sum of other degree vector spaces. And in particular, this equivariant map that establishes this isomorphism is well known, and it's called the transvectant. And I'll just give the form of it here. It's not too important. It's sort of this whole messy shebang working with derivatives and symbolic variables and such. But the important thing is A, that it's known and it's linear and we can compute it. In fact, we can pre-compute it. And roughly, again, we're taking as input two homogeneous polynomials and we're outputting another homogeneous polynomial. So this is the, you see this index n in the transvectant. this is indexing sort of which vector space we're looking at the decomposition into. Basically, the high level is that when we take a tensor product, we know how to decompose back into irreducible representations using an existing map called the transvectant, and it's a linear map, and we can compute it. That's really the important thing. And I don't want to belabor the architecture too much more. So I'll just say, what have we done so far? Again, I understand this might be a little bit of a lot to take in if you haven't seen these architectures before, but let me try and summarize. So as input, we have a polynomial. Let's separate it out into the different degree homogeneous parts. And in fact, now we have different vectors that live in different irreducible representation spaces of SL2R. As our nonlinearity, we take tensor products between all of these, like every possible pair of vectors, and then we use the Clebsch-Gordon decomposition to basically linearly decompose these pairwise tensor products back into the vector spaces of degree, the different degree homogeneous polynomials. So these sort of first two columns are describing like the overall nonlinear operation from irreps to irreps. And then we also use Schur's lemma, basically just throw in some learnable linear matrices. And we also, again, get activations, which are still irreps. And everything so far here has been equivariant to SL2R. So if you apply a change of variables to the input polynomials at every single layer of this network, the intermediate polynomials will also have that change of variable applied to them. And you might see this blue MLP box. And this is also pretty standard and also very intuitive, which is that the degree 0 irrep is basically just invariance. And if you have some invariants, you can do anything that you want to them. You can apply any nonlinear function, doesn't have to be a polynomial, doesn't have to be linear, and you'll get out more invariants. So let's just throw them into an MLP, a multi-layer perceptron, totally general, and get out some new invariants for hopefully some additional expressivity. So we've built this architecture, and indeed we actually did build this architecture, and it really is equivariant to SL2R, which might be, at least to us, was cool that we could do this for a group that's as non-compact and large as SL2R. I guess I haven't described to you yet how you go from polynomials to matrices, right? Because ultimately we want this matrix that like verifies positivity of the polynomial. This is again, mostly standard ingredient, but sort of with a twist for our problem. So we're going from a collection of homogeneous polynomials via a linear equivariant map to an output matrix. And this is sort of some conversion between representations that's fairly common. But we want to enforce these anti-diagonal sums of the output matrix. And it turns out there's a very like neat and elegant way of doing this. At the high level, we're just sort of like restricting this mapping so that it's still equivariant, but these anti-diagonal sums hold. More specifically, again, you can sort of check the details of this in the paper. You sort of add some kind of a skip connection of the original input polynomial, and we choose some particularly nice interpretable form of L such that the output matrix has the correct anti-diagonal sums. So this is maybe less standard for equivariance, where we don't just want to be equivariant, we also want the matrix to have the correct anti-diagonal sums. And if you remember, sort of the things that we care about are not just representing the polynomial, but also being PSD. The PSD property is what has to be learned. So there's no way of actually enforcing this because you could give the network something that's not positive, and there's no way there actually is it. There doesn't exist a PSDQ. So the positive semi-definiteness is what we're hoping is learned from the training data, all of this training data that was generated by convex solvers on actually positive polynomials. But we're at least enforcing that when I give you this matrix Q, it really does represent the polynomial that you gave it as input. Right, okay. Again, feel free to mention questions if anyone has any.
So in the original formulation, you're optimizing some like a log determinant subject to this PSD constraint.
Right. Mm-hmm.
Where does the log determinant show up in the neural net formulation?
So the log determinant doesn't show up in the neural net formulation. It shows up in the training data, in that we have to pick, you have a bunch of training data, which is polynomials, and I have to give you a and that we've generated them, so they're all positive. And you need to associate labels, AKA positive semi-definite matrices, with these polynomials. And the way we get that is by solving the convex program associated with the maximum log determinant. So that's the function we're trying to get the network to approximate.
I see. So both the optimizer is that's the thing you're trying to predict using the neural net. The training set is cooked up in such a way that it satisfies the feasibility condition and it also optimizes the objective function. I see.
Exactly. Yep, that's
Okay.
right. That's right. Yeah, I'm sorry, I moved through that perhaps a little too fast, but that is the important thing, is that the training data is coming from a solver on this maximum log determinant formulation. We're hard coding the equivariance, we're hard coding this sort of equation on the slide title, but the positive semi-definiteness, and in particular having maximal log determinant, is what we're hoping the network will learn based on the training data. Yeah, thank you so much for that question. So we've gone to all this effort of building this architecture and training it on all of these convex solves. And so we actually did this, and it didn't work that well. And we thought for a while about, why is this not working very well compared to like a baseline, which is just, a fully connected network with no equivariance, no structure, no intelligence, just, sort of trained on the training data. Why isn't this equivariant network working super well? And after basically a very long time, we revisited this question of expressivity. And so again, just generally, when you're designing a new neural network architecture, there's a very classical, I would call it a sanity check, that is typically done for neural architectures, which is universality. So even outside the equivariance literature, you can just ask, I have some family of architectures, and it has some knobs I can turn, which is typically like how large the width of the network is or how many channels it has. If I turn this knob sufficiently and I'm allowed to choose any parameters for the network, can I arbitrarily well approximate any continuous function? That's the traditional universality thing, and there's sort of all these old results by Aaron and other people that show like just standard MLPs are universal. And that was great. Of course, it's not sufficient for being a good architecture, but it's a pretty good sanity check, because if you can't even represent the function that you're trying to learn, sort of hope is lost. And this line of work has also been followed for equivariant architecture design. And the answer is typically yes, and it typically proceeds, much like the non-equivariant literature, via a polynomial approximation argument. And I just want to be really cautious here. So we're using polynomial in two different ways. There's this idiosyncrasy of the problem, that the inputs to our problem happen to be polynomials. It's just a data type. When I say polynomial here, I mean in the sense of approximating a function via a polynomial in the inputs. And so when we talk about polynomials here, a polynomial approximation means a polynomial in the coefficients of the input polynomial. So there's sort of two polynomials dancing around. Polynomial here is like the very standard polynomial that shows up in approximation theory. And traditionally, there's some appealing to the Stone-Weierstrass theorem that says, okay, if I can approximate any polynomial, that's going to be good enough. And this has been done for a lot of equivariant networks by Yarotsky originally. More recently, however, there were a ton of non-compact groups that Bogatsky et al. In 2020 had these universal architectures, which basically had an identical architecture to what we've described for SL2R, just for different groups. So for example, they even cover SL2C, not SL2R. So we looked at this and we thought, okay, surely our thing is universal. And we thought this for a while until we realized it actually wasn't. And this is a sort of surprising contrast to all of this previous extremely analogous work that basically does the same thing for SL2C and other non-compact groups. And let me tell you the way that it's not universal now. So the counterexample that we have to universality is actually the exact function we're trying to learn. It is the maximum determinant function. So you can't say, oh, it's not universal, but it's like some funky, crazy function that it can't approximate. It turns out it's actually this function. So that sort of explains to some degree why it wasn't working super well. And the formal theorem is this. We have our function from before, we have our network with the architecture I sort of hand-wavily described. There exists an input polynomial and an absolute constant epsilon, such that regardless of the size and parameters of the network, we can never approximate that input polynomial better than epsilon in any like reasonable norm. And this means that the architecture we just went to some effort to build, and which also emulates a lot of universal architectures, is itself not universal. And so let me tell you a little bit, just the outline of the proof, but I think I'll sort of skirt over the details here. But basically it relies on looking at some property which is preserved through every layer of the architecture, which is called balancing. We basically give this definition for what it means for a monomial to be balanced, and then we show that every operation in the network preserves balancing. Again, I'm gonna, I think, skip through these details more for the sake of time. But the actual construction here, maybe let me just give you a flavor, is that if we look at this particular polynomial, which is x to the eighth plus y to the eighth, it satisfies this balanced property, whatever that is, which means that every output of the network is also going to be balanced. And in particular, that tells us some sort of restriction on what type of polynomials show up in the output of the network. And then we can look at the sparsity pattern that they have when we put them through this final last layer to get at a matrix. And the very high level thing here is that the sparsity of anything that the network can possibly output does not match the sparsity of the computed correct answer when we actually like sort of compute using a convex solver to very high precision what the sparsity pattern is supposed to be. And so this is a very, very high level idea, but the important thing is the result, which is that the maximum log determinant function of this particular input polynomial cannot be represented by our network architecture. And in fact, there's something stronger that we get out of this, which is that this function is not approximable by any equivariant polynomial. And this is really surprising. This means that like all of this Stone-Weierstrass theory doesn't actually help us here. So you might wonder like, okay, is this just a problem with how you defined your architecture? And what we want to say is largely no, because what we can show and thought was sufficient is that our network can approximate any SL2R equivariant polynomial using these transvectant operations. Therefore, if our network can approximate any equivariant polynomial, but it can't approximate this maximum log determinant function, the function itself cannot be approximated by any other equivariant polynomial. And so any approach to universality that goes via Stone-Weierstrass, which is basically, as far as I know, almost all of the universality and expressivity type results in this literature, will not work for sort of representing this function. Equivariant, there's a gap for SL2R between equivariant polynomials and equivariant functions overall. And unfortunately, this very exciting function lives in that gap. And it's not really a contrived or a natural function. It's actually the exact function that we care about in applications. And so this suggests that any hope of getting around this issue must use some sort of fundamentally different paradigm. And again, this is pretty different from previous work and was like quite surprising to us. And I'll mention, I think at the end, some ideas we have for how you could maybe still hope to use equivariance. In fact, well, I'll discuss one that we've done and a couple others that we're excited about. So you might ask like, okay, again, this is really weird. We're saying that there's this interesting equivariant function that can't be approximated by equivariant polynomials, like to arbitrary precision. What has gone wrong? And we're still not entirely sure, but we have a couple key differences that we can point out. So one property is that the hard function f is only defined on positive polynomials. It's not defined on all inputs. We suspect this isn't the problem because universality statements usually only work with sort of approximation on like a compact set anyway at a time. But this is at least one difference from, for example, the Vygotsky et al. Paper that shows usually like if you have equivariant polynomials, this will be good enough for all continuous equivariant functions. We also critically are working with SL2R instead of SL2C. And when we dug around a bit in this literature, the sort of key difference is that most of these past universality proofs rely on working with a maximal compact subgroup and having this maximal compact subgroup essentially take into account the behavior of the whole group. So in the complex case, this would be SO2C, and somehow like the invariants with respect to SO2C and SL2C are basically the same. Like SO2C captures the important behavior. However, for SL2R, this is not the case. So the maximal compact subgroup is SO2R, but it's very easy to see that there are values which are invariants under SO2, but not SL2. And so this is sort of seems to be the critical step where at least previous work on SL2C breaks down for SL2R, which they might seem super similar, and in many ways they are, but in this way they are not. So what should we do? Should we throw out all of this knowledge of SL2R? We say no, let's do something else. So instead, we're going to fall back to this tried and true method, which is very ubiquitous in computer vision by a color shift in other equivariance literature sometimes too, which is just data augmentation. So for each training point, you apply a random transformation. In the vision world, this would be like a crop or a color shift. In the equivariance world, this is a group transformation. And instead of giving your network the original training data, you give it this transformed training data. And this doesn't really add computation time, at least significant computation time, because you can compute exactly the correct answer without resolving a convex problem. So it's basically like giving you a function value at another point on the orbit of your original input training point. Now, the reason we originally didn't do this is because it doesn't enforce equivariance strictly. And we really wanted strict equivariance because for compact groups, this seems to be the name of the game. But it does have some advantages. And sort of overall, I think one of the takeaways of this work is that for SL2R and non-compact groups, data augmentation might just be the way to go. which is that, first of all, it has worked very well in other domains, not just equivariance. And it's also very easy to combine with any architecture and doesn't really involve any new complicated like normalization or optimization or engineering concerns that you also run into when you tend to build these like tensor product equivariance architectures.
Is there an
Um,
obvious choice of measure? Oh, you're right there. Got it.
well, yeah, I mean, yes and no. The obvious like necessary but not sufficient choice for measure is to make sure you're not generating really ill-conditioned elements of SL2R, because then when you apply this data augmentation, like this induced matrix is going to be horribly ill-conditioned and you're basically just going to get garbage as your augmented data point. So we pick some measure over SL2R based on I forget the name of the parameterization. Basically, we put some like fairly arbitrary distribution over SL2R, but we throw out basically anything that comes from the distribution that doesn't have condition numbers in a specified range where we're pretty confident that for the degrees that we're testing, the condition number is not so bad that it like results in numerically meaningless results. There could also be like more interesting questions you could ask about what is the right distribution to augment with, because again, because this is a non-compact group, like any distribution you choose will induce a shift from the original training distribution. And so the question is like, what shift do you care about? Maybe that will be application dependent, but that's not something we've gone too far into. But let me finally start to show you one plot that hopefully summarizes up how these different methods stack up. But what do we end up testing? Well, we'll still test the SL2 net, like just for completeness, and because we originally tested it before we figured out that it actually wasn't universal. We also test equivariance to the maximal compact subgroup, which is SO2R. And then we also try augmenting in the way that I just described, where you basically sample a random element of SL2 or SO2 and apply it to your training data. And so the augmented approaches are not precisely equivariant. And we can also compare this to just a very vanilla MLP that has no knowledge of equivariance at all. And so for the stage of this paper, we have worked with synthetic data. It would be exciting to sort of track someone down from the robot world who can give us more real data on this, but we're going to just generate our data. The data will consist of only positive polynomials, again, because there's not really a meaningful label for non-positive polynomials. And if a polynomial isn't positive, we can't really expect the network to output something reasonable anyway. So basically, we come up with some fairly reasonable way of generating positive polynomials. Then we compute the labels, again, using this sort of time-consuming convex optimization method. And this is our training data. And okay, this is a fairly dense plot, so let me try and highlight the important things. And I understand it may be a little hard to see, for which I apologize. But basically what we're showing here on the y-axis is the test error. So error on unseen instances that were not on the training data. The y-axis covers the degree of distribution shift. So the leftmost point is the original test data set, which is generated according to the distribution that I put on the previous slide. As you move further to the right on the x-axis, we're applying random SL2 transforms, which are conditioned with condition number in a certain range. So intuitively, they're stretching out. The change of variables is more dramatic the more you move to the right on the x-axis. So as you move to the right on the x-axis, you have increasing test distribution shift. You can also, I guess I didn't include it, but there's some pictures with this where like when you're applying this change of variables to a circle, the higher the condition number of the induced SL2R transform, like roughly like the more it gets squished into like a super long ellipse. So somehow the more you go to the right on the x-axis, the harder of a distribution shift it is. And what we see overall is that what works the best is using a traditional MLP with augmentation, where as long as the condition numbers of the SL2R transforms are in a pretty low range. So this orange line is the MLP augmented by random special linear group transformations that have condition number between 1 and 3. When you get up to condition number like 5 to 7, that is fine on its own, but when you take these induced matrices, they have horrendous condition number because remember, it grows exponentially, and this suddenly gives you this top line, which is the absolute worst. The SL2 net is the second worst, this blue line. So the lack of universality really does seem to be having, whether it's that or in addition something else, but it's not performing super well. We see that what's sort of across all of these levels, the most robust SL2R distributions is just doing a regular MLP with data augmentation. So this is a sort of surprising result to us. But one, I think, really high level takeaway that's even like a little bit separate of the equivariance is to note that just across the board, the MLP is way faster than a convex solver. So even without thinking about equivariance, without thinking about data augmentation, just looking at forward passes, this hopefully validates that this is an interesting direction to go in. Obviously, you're putting in extra time to train the MLP, but when it comes time to look at a fresh example, you're getting a significant speed up, even from this distribution that we sort of contrived and maybe isn't incredibly complicated. So here SES is a first order solver, so it's supposed to be even faster than the solver that we use to generate the data set. But we also compared this to the solver times to actually generate the data set. And it's just orders of magnitude difference at still a very low error. So NMSE here is the normalized mean squared error. And we see that we're basically still getting verifiers out just way faster. And it's really taking advantage of the fact that our training distribution was generated not in like a uniformly random way over some ball of polynomials, but in like a very structured way. So the trained MLP has a much faster forward pass than the solver at the same error. And we do even better when you augment it in training using this equivariant structure. So I will just mention a couple conclusions and then future work, and then we'll be happy to take questions. So overall, what did we learn from this adventure? First and foremost, machine learning seems to be a promising avenue for accelerating polynomial problems. Obviously, this is very preliminary. Really, it should be distribution dependent, and so it will be important to verify this on other synthetic distributions, or more importantly, we do actually test this on a couple other distributions in the paper, which I encourage you to check out. But most importantly would be getting real data. Nonetheless, hopefully this is like an interesting avenue for accelerating these polynomial problems that hasn't really been addressed before, even with a really simple architecture. So I cannot emphasize enough that this MLP was not optimized like architecturally. It was just like a couple layers of fully connected linear layers interspersed with nonlinearities, and it already harnessed patterns in the data set very well in a way that's just not built into the way that convex solvers are formulated. They're solving every problem from scratch, which is both good and bad from a speed perspective. Another takeaway is that if you're working with a non-compact group, it can be extremely subtle, even when there are strong analogies to compact groups from a representation theoretic perspective. And indeed, any approach to like strong, precise SL2R equivariance is going to have to get around this polynomial problem. Like it's going to have a way of producing equivariant functions which are not polynomials in whatever your input space is, which is a pretty stringent requirement that's sort of implied by a universality result for any future people who are interested in SL2R. And finally, data augmentation, simple but friendly, is currently the best, like approximately equivariant option that we have for this group. There are definitely a lot of future directions here. So the most obvious question is, okay, how do you get around this loss of expressivity? One direction that could be interesting and maybe is related to some really cool work that Dustin has would be, for at least for invariant problems, maybe there's a way to use separators or have some sort of equivariant analog of those. Maybe there's some just like extra non-polynomial featurization that you need to compute and input to the network. But overall, this is like a hard direction, but an interesting one that might require like a fundamentally different architectural paradigm from what's used in most previous work. The other exciting future direction is, of course, in the applications direction. So we're claiming that this could be a way of getting like a really almost free like speed up on a lot of solver calls, but we have to actually get our hands on some of this non-synthetic data, as well as extend this work for having not bivariate polynomials, but multivariate polynomials, which often come up in applications and would be at least very straightforward from a data augmentation perspective. So yeah, that's everything I wanted to say. Thank you so much for your attention, and definitely Mitchell and I are both happy to take questions.
All right, let's thank the speaker by smashing that reaction button.